Okay, so have you ever like plugged in your phone charger and thought, wait a minute, how does this even like work?
Yeah. I mean, how does that power from the wall, actually charge up our phones and stuff like that without causing sparks and stuff?
Yeah, exactly. I mean, think about it. Like, how does a tiny little microphone pick up a whisper
Yeah.
and then suddenly blast it through these giant stadium speakers?
Right. It's like magic almost.
Yeah, so that's kind of the magic we're gonna dive into today, right?
We're going to pull back the curtain on those like basic building blocks, the electronics behind all this cool technology we use every day.
Yeah, exactly. And we really want to demystify three pretty crucial elements today. We've got BJTs, which stands for bipolar junction transistors.
Okay.
We've got rectifiers,
Mm-hmm.
and then we've got op-amp circuits or operational amplifiers.
Right.
And we're going to do this in a way that's like clear and engaging, right? We don't want to make it too technical.
Yeah, definitely. We want to make sure everyone can follow along.
Exactly. So for this deep dive, we've got a couple of really interesting sources. First off, we've been looking at the BTech Nationals Engineering Student Book.
Yeah.
And this is cool because it gives us a really practical look at these circuits, right?
Mm.
They talk about how they're simulated, how they're tested, all that good stuff.
That sounds useful.
Yeah. And then we also listened to a transcript from the Plug Into Electronics podcast, which is a really great, accessible overview of all of these topics. So
Okay, perfect.
let's jump in. Let's start with those BJTs, right? They're kind of the powerhouses behind boosting electronic signals.
Yeah, those BJTs, they essentially act as like a current gatekeeper with three terminals, right? So imagine it like a water tap, which is an analogy the podcast used.
Oh, I like that. Okay.
Yeah, so that small turn you give the tap handle, that's like a small current flowing into the base terminal of the BJT.
Gotcha. Okay.
And that small action then controls this much larger flow of water through the pipe, which corresponds to the path from the collector to the emitter.
So the collector and emitter are the other two terminals.
Exactly. So we've got the base where the control signal comes in the collector, which is usually associated with a higher voltage, and then the emitter at a lower voltage.
Okay, so that base current, it has a huge influence on the current flowing between the collector and the emitter.
Right, it does. And that's essentially what we mean by current amplification.
Right, because it's amplifying that smaller signal into a larger one.
Precisely. And speaking of amplification, our engineering textbook, the BTech Nationals Engineering Student Book, mentions this configuration called the common emitter configuration,
Okay.
which is super versatile. It can boost both the voltage and the power of a signal.
Oh, wow. Okay.
And they even talk about its use in what's called a Class A amplifier.
Right. And, thinking about the practical side of this, the Plug Into Electronics podcast gave this perfect example of a weak signal from a microphone.
Right.
So on its own, that signal's way too faint to drive headphones. You wouldn't be able to hear anything.
Yeah, you'd need some serious boost.
Exactly. And that's where the BJT amplifier steps in and takes that tiny signal
Right.
and amplifies it so we can actually hear it through the headphones.
Right. So it's not just about making things louder, it's about making those barely their signals actually usable.
Exactly. And I love this analogy from the podcast. They said, BJT doesn't create energy, it controls it. It's like a light switch with a dimmer.
That's a good one. Yeah.
Right. Because it's not generating power from nothing.
Yeah.
It's just cleverly managing that power that's already there.
Right. Right.
Now, I did notice in the BTech Nationals Engineering Student Book, they talk about three main ways to connect a transistor.
Oh, right.
There's the common emitter, which we've been talking about, but there's also common base and common collector.
Mm-hmm.
But the book does say that the common emitter setup is the most common one we see in electronics.
Yeah, it offers this really good balance in terms of amplification.
Right. So for a BJT to function as an amplifier, or even just a simple on-off switch, it needs to be biased correctly, right?
It does, yeah. The BTech Nationals Engineering Student Book explains this by saying the base collector junction needs to be reverse biased,
Okay.
and the base emitter junction needs to be forward biased for the transistor to conduct and amplify.
So it's like setting the stage for the transistor to do its job.
Exactly. And biasing just means applying the right voltages to these junctions, so it's in that active region where it can amplify the signal cleanly.
Gotcha. And the book mentions that when the transistor's fully on, this is called saturation, right?
Yes, and the base emitter voltage is approximately 0.7 volts in that state.
Okay. And then there's cutoff where no current flows.
Right, that's essentially the off state.
Exactly.
Yep.
So BJTs aren't just for boosting signals, they can also act like switches.
Oh, right, turning current on and off.
Yeah, and the BTech Nationals Engineering Student Book mentions a safety tip when using them as switches for inductive loads,
Okay.
like relays, which are basically electrically controlled switches.
Hmm.
So you almost always need to include a reverse bias diode.
Across the relay.
Yeah, to protect against something called back EMF, which is like a sudden voltage spike that can damage the transistor when the current is switched off.
Right, it's like a safety valve.
Exactly. So it's a tiny component, but it's super important for making sure the circuit is reliable.
I see.
Okay, so we've talked about making signals stronger. Now let's talk about how we power those devices.
Like the energy behind it all.
Exactly. So let's dive into rectification, which is basically transforming that AC power from your wall outlet into DC power, which is what most electronics actually use.
Right, because our devices need that steady, direct current.
Exactly. So the Plug into Electronics podcast mentioned two main types, half-wave and full-wave rectification.
Yeah, let's start with the simpler one, half-wave rectification.
Okay.
As the name suggests, it only allows one half of that incoming AC wave through while blocking the other half.
So it's either the positive part or the negative part.
Right, and the BTech Nationals Engineering Student Book says this is done with just a single diode.
And that diode only lets current flow in one direction.
Exactly. The podcast had this great visual for it.
Okay.
Imagine bouncing a basketball and only catching it on the way up. You're
Yeah.
essentially only using half of the energy of that bounce.
Oh, that's a great analogy.
Now, the textbook also mentions a crucial spec for the diode. It needs to be able to handle the peak inverse voltage, or PIV.
Okay, and what's that exactly?
So that's the maximum reverse voltage the diode will experience when it's blocking the other half of the cycle.
Gotcha. So it needs to be robust enough to handle that reverse voltage.
Exactly. If the PIV rating is too low, the diode could fail.
Right. So it sounds like while half-wave rectification is simple, it might not be the most efficient way to do things.
Yeah, that's where full wave rectification comes in. It's
Yeah.
more efficient because it actually uses both halves of that AC waveform.
Oh, interesting. Okay, and how does that work?
Well, the BTech Nationals Engineering Student Book describes two common methods for achieving full wave rectification. The first method uses a center-tapped transformer and two diodes. What's interesting is that the voltages across each half of the transformer's secondary winding are always in opposite phases.
Okay.
So during one half cycle, one diode conducts and lets current flow through the load.
Gotcha.
Then on the next half cycle, that first diode switches off and the second diode takes over,
Okay.
directing the current through the load in the same direction.
So no matter which half of the cycle it is, the current's always going the same way.
Exactly. And you end up with a pulsed DC output with twice the frequency of the original AC supply.
Oh, that's pretty clever. But the book did mention that each diode in this setup needs to handle twice the PIV of a single diode in a half-wave rectifier.
Right, because they're dealing with higher voltage swings.
Yeah, so that's a big difference.
It is. Now, the second and probably more common method for full wave rectification is the bridge rectifier.
Okay, and what does that one look like?
So this one uses 4 diodes connected in a specific way. And on each half cycle, a pair of diodes conducts, steering the current through the load in the same direction.
So again, it doesn't matter if the input's positive or negative. The current's always flowing the right way.
Precisely.
Oh, and the book also mentions that a lot of power supplies actually use a bridge rectifier block.
Yeah, those are handy. It's basically those 4 diodes all in one component.
Right, so that simplifies things a lot.
Definitely. So whether it's the 2-diode and transformer setup or the 4-diode bridge, full wave rectification gives us a much smoother and more efficient conversion to DC.
Right, getting us closer to that stable power our devices crave.
Now, even with full wave rectification, the output isn't perfectly smooth.
Oh, right. Okay.
It still has some ripple.
So it's not perfectly flat.
Right, and that's where smoothing comes in.
Okay, and what does that involve?
So typically, a reservoir capacitor is connected across the rectifier output.
Okay.
And this capacitor charges up to the peak voltage during the rising part of the wave and then discharges during the falling part.
So it's filling in those gaps.
Exactly. It smooths out the voltage dips and reduces that ripple.
Gotcha. It's like a little energy reserve to keep things stable.
And the BTech Nationals Engineering Student Book actually goes on to talk about using smoothing filters,
Okay.
which are combinations of capacitors and inductors and even Zener diode regulators to further refine the DC output.
Wow. So there are even more ways to fine-tune the power.
There are Zener diodes are specially designed to maintain a stable voltage across them when they're reverse biased.
So they're perfect for regulation.
Exactly. And the book even has a calculation example to work out the minimum value for a series resistor, which is used to protect the Zener diode.
That's super practical.
It is. So essentially we start with that AC from the wall outlet, use diodes to rectify it, smooth it out with capacitors, and potentially regulate it further with Zener diodes.
And that gives us the clean, stable DC power that our devices need.
Exactly. As the Plug-in to Electronics podcast summed it up, your laptop charger uses a full-wave rectifier to power up your device safely and smoothly.
It really is amazing how much goes into getting that steady power.
It is. Okay, so we've covered signal amplification and AC to DC conversion. Now let's move on to op-amps, or operational amplifiers.
Right, op-amps. The Plug into Electronics podcast called them electronic brains.
Which is pretty accurate.
They are. They're so versatile, they can boost signals, compare voltage levels, even do math within circuits.
Yeah, they're multi-talented.
And the BTech Nationals Engineering Student Book says a single op-amp chip can contain like 20 transistors.
Wow, that's a lot packed into one tiny chip.
It is. So the basic symbol for an op-amp shows two inputs.
Right, the inverting input with a minus sign and the non-inverting input with a plus sign.
And then there's a single output.
Exactly.
Now, the podcast focused on using op-amps for amplification in two main ways, inverting and non-inverting.
Right, let's start with the inverting amplifier.
Okay, so in an inverting amplifier, the input signal goes into the inverting input.
Yes, and at the output, the signal is flipped 180 degrees out of phase.
Okay,
And it's also amplified.
gotcha. So it's kind of like mirroring and boosting the signal.
Exactly. And the BTech Nationals Engineering Student Book gives us the formula for the gain of an inverting amplifier. It's R2R1.
Where R2 is the feedback resistor and R1 is the input resistor.
Right, and the negative sign means the signal is inverted.
Oh, right, of course.
The book also introduces this concept of a virtual earth at the inverting input.
Got it.
So due to the high gain of the op-amp and the negative feedback, that input is held at almost the same voltage as the non-inverting input, which is often ground.
Even though it's not directly connected.
Exactly. It's a pretty handy concept for analyzing these circuits.
Okay, so now let's look at the non-inverting amplifier.
All right, so with this one, the signal goes into the non-inverting input, and the output signal is in phase with the input, so no flipping this time.
Okay, but it's still amplified.
It is. And the BTech Nationals Engineering Student Book gives the gain formula for this as 1 plus R2R1.
Again, R2 is the feedback resistor and R1 is connected to the inverting input and ground.
Right. And something to note here is that the gain for a non-inverting amplifier is always 1 or greater.
Oh, interesting. Okay.
Now, the Plug into Electronics podcast actually gave some cool examples of where you might use these configurations.
Oh, like what?
So for the non-inverting amplifier, they mentioned buffering a signal,
Okay.
which is basically amplifying the signal's current without changing its voltage or phase.
So it makes it stronger without changing its characteristics.
Exactly. And for the inverting amplifier, they suggested flipping and boosting an audio signal for a speaker.
Okay, so you could use that to drive a speaker?
Precisely. And I loved their analogy for the op-amp. They said, think of an op-amp as a coach with a whistle. It can amplify the player's performance, and sometimes it even tells them to play in reverse.
That's a good one. It really captures the essence of what they do.
Right. Now, the BTech Nationals Engineering Student Book also mentions the really high open-loop gain of op-amps.
Okay, remind me what open loop gain is again.
So that's the amplification they provide without any external feedback components. And it can be massive. That's why in real circuits, we use negative feedback, often through those resistors we've been talking about, to control the overall gain of the amplifier and make sure it operates in a stable and predictable way.
Right, so we're basically reining in that huge gain with the feedback.
Exactly.
Okay, wow, we've covered a lot of ground in this deep dive.
We have.
We talked about BJTs and how they boost signals, then rectifiers, and how they convert AC to DC, remembering the difference between half wave and full wave.
Right. Half wave uses one half of the AC wave, full wave uses both.
Exactly. And then finally, those versatile op-amps with their inverting and non-inverting amplification capabilities.
Now, to help you remember all this, let's revisit those quick quiz questions from the podcast.
Okay.
First one. Which electronic component allows current to flow in only one direction?
That's got to be the diode.
Correct. Next, which input terminal on an op-amp flips the phase of the input signal?
That would be the inverting input, the one with the minus sign.
You got it. And last one, what is the main advantage of full wave rectification over half wave?
Full wave is more efficient because it uses both halves of the AC wave.
You nailed it. So now as you go about your day, think about all the electronic devices you use, your phone, your laptop, your TV. Try to picture those BJTs boosting those tiny signals, the rectifiers, providing that clean DC power, and the op amps shaping and amplifying everything.
It really makes you appreciate the complexity hidden inside these everyday gadgets.
It
And
does?
maybe next time you're feeling curious, you could even look up circuit diagrams online or research specific applications of these components.
That's a great idea. There's a whole world of electronics out there to explore.
Exactly.
And understanding these basic principles really gives you a deeper appreciation for the technology that's all around us.
It's like unlocking the secrets of the digital world.
It is. So keep that curiosity going and see what other fascinating discoveries you can make.
Plug into that curiosity.
Exactly.
Awesome. Well, thanks for joining me on this deep dive.
It's been a pleasure.
And until next time, keep exploring.
Keep on learning.